Welcome, students. In this video lecture, we are going to study the topic of conditional probability. Sometimes we know for certain that some events have already occurred, and this may have an effect on the probability we are trying to find. In other words, let's assume we are looking for probability of some event A, and if we know for certain that some other related event B have already occurred, then we might want to update our probability we are searching for. Let's take a look at the following example. Let's say your experiment consists of throwing a die single time. Number of outcomes in your sample space are 6. So these are numbers from 1 to 6. And if you are looking for probability of an event A of getting number 6, then we know that probability of that event is equal to 1 over 6 if we are tossing a fair die. Let's say that someone gave you an insight and told you that the number that have occurred on your toss is an even number. Let's call an event B as an event of getting an even number on your toss. With this information, we might want to update the probability we are looking for. This information has an effect of shrinking our sample space. So we might want to move from our original sample space S into the new one. Let's call it S prime. So we know that event B, even number, has occurred, meaning that there are three outcomes in our new sample space S prime. These outcomes are numbers 2, 4, and 6. So this is an event B. Okay, now if we are looking for probability of getting number 6 in that sample space, it's going to be equal to 1 over 3. The symbol P A given B reads probability of A given B. Now let's take a look at general example and let's try to derive the formula for this conditional probability of event A given B. Let's say we have sample space S, and let's assume that there are n outcomes, equally likely outcomes in our sample space. Total number of outcomes in our sample space is small n. We have an event A and event B. Let's assume that there are A number of outcomes in event A and B number of outcomes in event B, and C number of outcomes in their intersection. Let's say we are looking for probability of event A given B. Probability of event A given that we know that event B has occurred. Then following the argument in our previous example, this probability is going to be given by the following formula. So the number of outcomes in our new sample space. So let me draw our new sample space. Is B. So the total number of outcomes in our new sample space is B. Let's call this sample space as S prime. Now we are looking for the part of A in B, which is exactly their intersection. There are C number of outcomes in their intersection, meaning that this probability of A given B is equal to the following ratio of C over B. All right, now we can express this ratio as follows. We can artificially divide both numerator and denominator by n. Now, C over n denotes probability of their intersection, and probability B over n is probability of event B, which gives us a formula for conditional probability of event A given B. Now let's take a look at a couple of examples. We have two events A and B. They are defined such that probability that A occurs but B doesn't is 0.2. So probability of A occurs but B doesn't. So A intersection with B complement is given as 0.2. Probability that B occurs but A doesn't is 0.1. So probability of B intersection with A complement is given as 0.1. Probability that neither occurs is 0.6. So by neither occurs, we mean everything outside of their union. So A union B complement is given as 0.6. What is probability of A given B? We are searching for conditional probability of A given B, which is equal to probability of their intersection over probability of B. We don't know both numerator, we don't know denominator. Let's start by finding probability of their intersection. All right, so we know probability of complement of their union, meaning that probability of their union is equal to 1 minus 0.6, which is equal to 0.4. Now, let's take a look. I know these two values. Let's take a look at the following Venn diagram to make it clear. We have event A, event B. Let's color this part in blue. So A intersection with B complement is everything inside of A except its intersection with B. Let's color it in blue. B intersection with A complement is everything inside of B except its intersection with A. And let's color in yellow their intersection here. All right, then we can express probability of A union B as the union of these three mutually exclusive regions, meaning that probability of A union B is equal to probability of A intersection with B complement, this is blue region here, plus probability of their intersection, that yellow region here, plus probability of B intersection with A complement, which is represented as red region over here. Okay, so from this equation here, the only unknown is probability of their intersection, which might be expressed then as probability of their union, which is 0.4, minus probability of A intersection with B complement, 0.2, minus probability of intersection B intersection with A complement, which is 0.1. So probability of their intersection is equal to 0.1. Next step, we found our numerator. It is equal to 0.1. Now, denominator is still unknown, but it can be expressed as the union of the following two regions of red and yellow one. Two mutually exclusive regions, meaning that we can express probability of B as the sum of the following probabilities. Probability of B intersection with A complement plus probability of their intersection, A intersection with B, which is 0.1 over 0.1 plus 0.1. So this conditional probability A given B is equal to 0.5. Okay, great. Now let's take a look at the next example. Mountain resorts A and B are connected by the following highways represented here. First one is a direct route from A to B through highway E1. Second one is a route through the third mountain resort C, connected through highways E2 and E3. During the winter season, however, due to heavy snow and ice, some of these roads might be closed. Probability that road E1 will be open is given as 2 or 5. Probability that road E2 will work is 3 or 4. E3 will work is 2 over 3. Also, we know that probability that road E3 will be working given that E2 is working is given as 4 or 5. Probability that road E1 will be working given that E2 and E3 are working is given as 1 over 2. What is the probability that traveler will be able to get from A to B? So we are looking for the following probability. Traveler being able to get from A to B means that either E1 works or E2 and E3 work at the same time. So we are looking for probability of the following union. All right, guys, before moving on, let's recall our formula for conditional probability. Let's say we are looking for conditional probability of event A given B. It is equal to probability of A intersection B over probability of B. Probability of B given A is equal to probability of, again, A intersection B divided by probability of A. So from the following two expressions, we can see that we can define probability of A intersection B using the following two ways. First one is using conditional probability of A given B multiplied by probability of B. And second way is that we can express probability of the same intersection as probability of B given A multiplied by probability of A. So if we would like to express our probability of intersections, then we have two ways to do it. An easy way to not mess up these conditional probabilities is to use the following simple rule. The mathematic notation here is absolutely wrong, but it's a nice way to remember it. You can consider this conditional probability sign as a division sign. So these two should cancel out. And in the first case, probability of A given B multiplied by probability of B. So these two should cancel out. But the notation here is completely wrong. Okay, now back onto our problem. We might express the probability of their union in the following way. Probability of E1 plus probability of E2 intersection with E3 minus probability of intersection of these two events minus probability of E1 intersection with E2 intersection with E3. You can actually remove these brackets here. It will make no difference. Now we know the probability of E1. We'll leave it as it is. We do not know probability of E2 intersection with E3, which we can express in the following two ways. First one, we can express it as probability of E2 given E3 multiplied by probability of E3. However, from the conditions of our problem, I do not know conditional probability of E2 given E3, but I do know probability of E3 given E2, meaning that I would like to express it as, so let's leave it as probability of E1 for now, as probability of E3 given E2 multiplied by probability of E2. Next, here, let's take a look at the conditions of our problem and let's see what is known for us. So we know probability of E1 given probability, so we know conditional probability of E1 given intersection of E2 and E3. So we can express this probability of intersection as probability of E1 given E2 intersection with E3 multiplied by probability of E2 intersection with E3. So from conditions of our problem, probability of intersection E2 given E3, these are also unknown. However, we've already expressed it as probability E3 given E2 multiplied by probability of E2. So let's replace this one as probability of E3 given E2 multiplied by probability of E2. Now, this is known. This is also known. This is also known. This here is also given. That is also known, and this is also known.